Hi guys, so this is the part 2 of our last video which reviewed the 2023 Physics Regents multiple choice. Today we're reviewing the short response section, so let's get started. Base your answers to questions 51 through 54 on the information and circuit diagram below. An electric circuit contains a battery, a 3 ohm resistor, a 6 ohm resistor, and 3 meters. Ammeter 1 reads 6 amperes, ammeter 2 reads 4 amperes, and the voltmeter reads 12 volts. Determine the potential difference across the battery. So remember, that potential difference, this is just voltage. The circuit is parallel, and in parallel circuits, the voltage stays constant throughout the entire thing. So like the overall voltage equals voltage 1, voltage 2. So here, at this 6 ohm resistor, it says that the voltmeter reads 12 volts. So no matter what, across this entire thing, the potential difference will be 12 volts. 52. Determine the current through the 6 ohm resistor. So we have both the voltage and resistance, we just need to find the current. So we could just use the equation R, or resistance, equals V over I, voltage over current. So our R is 6 ohms equals 12 volts over I. And after we finish calculating that, we're going to get an I, a current, of 2 amps. 53 through 54. Calculate the equivalent resistance of the current. So to calculate the total or equivalent resistance, we're just going to use the parallel resistance formula, which is 1 over equivalent resistance equals 1 over resistance 1 plus 1 over resistance 2. So let's plug that in. So the first resistor is 3 ohms. So 1 over 3 ohms plus 1 over 6 ohms, the other one. And 1 over 3 plus 1 over 6 is just 3 over 6, which equals 0.5. So we're going to do 1 over 0.5, which is this. And that's going to equal 2 ohms. 55. The diagram below shows parallel straight wavefronts approaching a rigid barrier that has a small opening in its center. On the diagram in your answer booklet, draw 3 wavefronts after they have passed through the opening. So this question is about diffraction, because remember, diffraction is when the waves spread around an object once they go through the slits. So in this case, we just have one slit here, and after they go through the slit, they spread out and bend. So in our case, it should look something like this. It starts out small, but then the wavefronts get larger as they bend and spread out. Base your answers to questions 56 through 59 on the information below. A projectile is launched from level ground with an initial vertical speed of 26 meters per second upward and an initial horizontal speed of 15 meters per second. 56 through 57. Calculate the total time the projectile is in the air before the projectile returns to the level ground. So, let's write down all the information we have. For the vertical component, we know that it has an initial velocity of 26 meters per second. We also know that a constant is that acceleration is always just gravity, and in this case, it's going to be negative 9.81 meters per second squared. And we also know that the final velocity is going to be 0 meters per second, because once the projectile just lands back on the ground, it's going to have no velocity. And for the horizontal component, it says here that the initial horizontal speed was 15 meters per second. And we don't really know anything else right now. So, for 56 through 57, we need to find the total time. In this case, we have all these different components, so we could look at our different kinematics equations for something with all of them. And that equation is going to be Vf equals Vi plus At. So we just plug it in. Vf is 0. I'll write it over here. 0 equals Vi 26 meters per second plus negative 9.81 meters per second squared times time. So now we just subtract negative 26 on both sides. We're doing basic math. And after we do all that math, we should get time equals 2.65 seconds. And you might think this is the final answer, but it's not. Let me draw it out to kind of show you. So if the projectile starts here, it's this little circle. It's going to go something like this. And this 2.65 seconds just represents when it meets the halfway point. So it's like this. But that's not the total time that's in the air. So we have this whole other part, which is another 2.65 seconds. So we need to multiply this by 2. So 2.65 seconds times 2 is going to equal our new time, our real time, which is 5.3 seconds. That's the total amount of time that takes to reach the ground. 58. Determine the total horizontal distance the projectile travels before the projectile returns to the ground. So now we're using our horizontal components. We have a new piece of information here that the time is 5.3 seconds. So now we have velocity and time. So we could just use the equation v equals d over t. So 15 meters per second equals distance, what we're trying to find, over time, 5.3 seconds. So after we do the math here, we're just going to get a distance of around 80 meters, if you round. 59. Determine the angle above the horizontal at which the projectile is launched. So this question is a bit tricky because you need to remember that if it asks you for something about the horizontal, you have to use tangent. That's just a little thing you have to remember. So in this case, we're asking for the angle, so we need to use the inverse of tangent. So tan inverse. And it's going to be your vertical velocity over your horizontal velocity. So Vy over Vx. So in this case, that's going to be inverse of tan. Vy is 26, and then Vx is 15. So after you do that, you're going to get an angle of 60 degrees. Base your answers to questions 60 through 62 on the information below. A 20 Newton force due east and a 25 Newton force due south act concurrently at point P. The diagram shows a vector drawn to scale representing the 20 Newton force due east. Using a ruler, determine the scale used in the diagram. So, I don't have a ruler because I'm on my iPad, but if you just print it out and then you could measure it with a real ruler, then you'll get around 4 centimeters for this entire thing. For this 20 Newton vector, you're going to get 4 centimeters. So that's around a scale of 1 centimeter for every 5 newtons. 61. On the diagram in your answer booklet, use a metric ruler and the scale shown in the diagram to draw a vector to represent the 25 Newton force due south acting on point P. Begin the vector at point P and label its magnitude in newtons. I'm not going to do everything on the answer booklet. I'm just going to do it here. It should look something like this. Remember to label it 25 newtons. And this thing, maybe it should be a little bit longer actually, because this thing has to be about 5 centimeters. Because remember our scale, 1 centimeter equals 5 newtons. If it's 25 newtons, then it should be around 5 centimeters. 62. Determine the magnitude of the resultant force acting at point P. So, to find the resultant force, this is pretty easy. That's because it's giving us 2 vectors acting on a right angle, meaning we can use the Pythagorean theorem. So, a squared plus b squared equals c squared. And our a squared and our b squared are going to be 20 newtons and 25 newtons. So 20 squared plus 25 squared equals c squared. C is our resultant. So 400 plus 625 equals c squared. And after you finish up that math, you're going to get c, or the resultant, to equal about 32 newtons. '63. Determine the amount of energy in electron volts that must be absorbed by an energy atom to excite the atom from n equals 1 energy level directly to the n equals 4 energy level. So, in order to find the energy absorbed, we're going to use the equation E photon equals EI minus EF. And we can find our EI and our EF by just looking at the hydrogen table on the reference table. So our EI, or our n equals 1 energy level, is going to be negative 13.6. So we could just plug it in like this. E photon equals negative 13.6 minus our EF, which is our n equals 4 energy level, which is negative 0.85. Minus negative 0.85. So that's going to end up being negative 12.75 EV. But it's actually not negative 12, it's positive 12. And even though the math says it's negative, it's positive because it's asking for the amount of energy that needs to be absorbed. So in order to get from negative 13.6 to negative 0.85, you have to absorb positive 12.75 electron volts. Do you guys see that? 64. Determine the sign and magnitude of the net charge in coulombs of a particle that has a core composition of BBB. So all you need to do here is go into your reference table and see that the charge of B is equivalent to negative 1 over 3. So if B equals negative 1 over 3, then BBB, which is just 3 B's, is just negative 1 over 3 times 3, which is going to equal negative 3 over 3, or negative 1. And what's the charge of something that's negative 1? That's just negative 1 E, which is an electron. So, to find what one electron is in coulombs, we have to remember that an electron is an elementary charge. So, if you look back at the reference table, one electron, or a negative elementary charge, is equal to negative 1.6 times 10 to the negative 19th. And this is in coulombs. 65. What type of electromagnetic radiation would contain photons each having an energy of 2.65 times 10 to the negative 20 joule? So, this question might throw you off, but remember that the electromagnetic radiation is just the different radiations on the electromagnetic spectrum in your reference table. So in order to figure this out, we just have to use the equation E photon equals HF. Because we already have the energy and H is a constant. So let's just plug it in. 2.65 times 10 to the negative 20 equals H, which is 6.63 times 10 to the negative 34 times frequency. So when you solve this out, where you're going to get frequency equals 4 times 10 to the 13th. And when you look back onto your reference table, you're going to see that this frequency is equal to infrared radiation. So now we're on to part C. Base your answers to questions 66 through 70 on the information below. A car initially traveling at a velocity of 25 meters per second accelerates uniformly at a rate of 1.5 meters per second squared east for 6 seconds. Calculate the magnitude of the car's velocity after 6 seconds. So, in this problem, we're already given VI, A, and T, and we just need to find F. As you see here, it's giving us velocity of 25 meters per second. So our initial velocity, 25 meters per second, and our acceleration, 1.5 meters per second squared, and our time is 6 seconds. So in order to find the final velocity, we just need to use the equation VF equals VI plus AT. So VF equals 25 meters per second plus 1.5 meters per second squared times 6. And after you do that math, you're going to get a final velocity of 16 meters per second west. '68. Determine the direction of the car's velocity after the 6 seconds. Once again, that's just west. If it's going west and there's nothing talking about force, then it's just going west. 69 to 70. Calculate the total distance traveled by the car during the 6 seconds. For this, we're just going to use another kinematics equation since we have all the needed components. I'm going to use the equation D equals VIT plus 1/2 AT squared. So we're just plugging it in. D equals VI, 25 meters per second, times time, 6 seconds, plus 1/2 times acceleration, 1.5 meters per second squared, times 6 seconds again, squared. And once you do all of that, you're going to get a distance of about 120 meters. It's going to be 123 meters exactly, but you're just going to round down. So, 71 through 76. Starting from rest at the top of the slide, a 40-kilogram child accelerates uniformly along the surface of a 4.2 meter long slide at a rate of 0.3 meters per second squared until she reaches the bottom of the slide. 71 through 72. Calculate the speed of the child at the instant she reaches the bottom of the slide. So, let's write down all the information that we have. For the vertical component of this problem, our VI is going to be 0 because the kid starts at rest. Remember that. And then we're also given an acceleration of 0.3 meters per second squared. And we're also given a distance of 4.2 meters. So for this first equation to find the speed when she reaches the bottom of the slide, or the VF, we just do VF squared equals VI squared plus 2AD. And plug it in. VF squared equals 0 squared plus 2 times 0.3 meters per second squared times 4.2 meters. And once you finish all that math, you're going to get VF, or final velocity, equals 1.6 meters per second. 73 through 74. Calculate the child's kinetic energy at the bottom of the slide. So, this is a simple problem. We just need to use the equation KE, or kinetic energy, equals 1/2 times mass times velocity squared. So just plug it in. 1/2 times mass, the child is 40 kilograms, 40 kg, times a velocity of, once it reaches the bottom, so that's this velocity, we're going to use 1.6 meters per second squared. And our KE, we're going to get 51 joules. Determine the total gravitational potential energy gained by the child when climbing 1.5 meters vertically from the bottom to the top of the slide. So this is another easy question. We're just going to do the same thing except with the potential energy equation. So PE equals mass times gravity times height. So in this case, that's going to be 40 kilograms times 9.81 meters per second squared times the height of 1.5 meters. And you're going to get an energy of 588 joules. 76. Determine the total amount of mechanical energy lost by the child slide system as the child slides from the top to the bottom of the slide. So remember, mechanical energy is just equal to PE plus KE. So in this system, there is 588 joules of potential energy and 51 joules of kinetic energy. So they're kind of like opposites. So if you have one thing, the other is reversed. So we have to negate one of them. So let's negate or just subtract KE minus 51. And you're going to get about 537. But we're just going to round that to 540 joules. That is the amount of mechanical energy lost. Base your answer to questions 77 through 80 on the information and diagram below. The diagram below represents a ray of light, F equals 5.09 times 10 to the 14th hertz, in flint glass incident on air at an angle of incidence of 30 degrees. 77 through 78. Calculate the angle of refraction of the light ray in the air. So in this problem, we need to use the equation N1 times sine 1 equals N2 sine theta 2. And we have to use this equation in order to find the angle of refraction of the light ray in air. We can plug in the numbers for this equation since we already know that the index of refraction for both flint glass and air because it's on the reference table. And it tells us the angle of the glass right here. So N1 is the index of refraction for flint glass, and that's 1.66. So 1.66 times sine 30 equals N2, which is air, so that's 1.00. 1.00 times sine theta 2. And after you finish doing this math, you're going to get sine theta 2 is equal to 0.83. So you're going to have to use the inverse of sine times 0.83 to get the angle, which is 56 degrees. Using a protractor and a straight edge, draw the refracted light ray on the diagram in your answer booklet. So I don't have a protractor or straight edge because I'm on an iPad, but it should look something like this. And then this angle here should be about 56 degrees. So this is the light ray after it gets reflected. No, sorry, not reflected. This is after it gets refracted once it enters the air. 80. State what happens to the wavelength of the light ray as the light ray passes into the air from the flint glass. So, the wavelength of the light ray increases. So the wavelength increases because as it passes into the air, the index of refraction gets smaller because the index of refraction of the flint glass is 1.66, while the air is only 1. So as that happens, the ray moves away from the normal. We could see that. Here it's closer to the normal. while here it's more far away. And because of this, we could tell that the light wave increases. The wavelength, sorry. Base your answers to questions 81 through 85 on the information, graph, and diagram below on your knowledge of physics. A student pulls a block weighing 2 newtons resting on a horizontal laboratory table with a string and force sensor. The sensor measures the force applied to the block when the block is at rest and when the block is moving. The force applied to the block is plotted against time on the graph. 81. Based on the graph, determine the force of kinetic friction acting on the block as it is pulled at constant velocity across the laboratory table. So the graph here shows us the relationship between the force applied and the time. And we could see that the constant velocity begins around here. This is where that happens. And that's because it's a straight line and the force doesn't fluctuate. It's just constantly at 0.9 newtons. And when something moves at constant velocity, that means the applied force is equal to the frictional force. Remember how F net equals 0 means that it's either at rest or constant velocity? Yeah. So here it says it's at 0.9 newtons. That's when it's at constant velocity. And if there's an applied 0.9 newtons, that means there's a frictional force of 0.9 newtons, since it's moving at constant velocity. 82 to 83. Calculate the coefficient of kinetic friction between the block and the laboratory table. So for this, we're just going to use the FF equals mu Fn formula. So FF, we have that right there, 0.9 newtons is equal to mu Fn, and our Fn is right here, it's just 2 newtons. 2. And after we finish calculating that, we're going to get a coefficient of friction, or mu, of 0.45. 84. At the instant the block begins to move, what happens to the value of the coefficient of friction? So the value is going to decrease. So let me tell you why the value decreases. It decreases because as the block begins to move, it takes less energy to keep it moving. It takes a lot more energy to make a block start moving than it does to keep something moving. 85. How would the coefficient of kinetic friction between the block and the laboratory table be affected if a 0.5 kilogram mass were placed on the block? So, it would remain the same. It would remain the same because the coefficient of friction only depends on the materials of the touching surfaces. So if you're putting a 0.5 kilogram mass onto the block, there's no difference. Like if this is the table and this is the block and you're just adding another 0.5 mass on it, this thing is only touching the block. It's not touching the laboratory table between that thing. So that means the coefficient of kinetic friction would not be affected. So this is the last question, meaning that we're ending off the session for today. The 2024 Physics Regents just dropped recently, so I will be reviewing that along with another person reviewing the Algebra 2 Regents if you guys are interested in that.